I'm going to show you a super close-up shot of this tiny glass vial. Looks totally empty, right? But now I'm going to cool it down. What you just saw is the element xenon condensing into a liquid. Okay, you can see it sloshing around. Now the xenon is about to change from a liquid into a mysterious, wild, wonderful, and useful sort of fourth state of matter, a supercritical fluid. And in fact, if I move the vial around a little bit, if you look really closely, you can see the supercritical fluid sloshing around. It looks kind of like heat waves in a desert. Xenon is not the only element or chemical that can go supercritical. Lots of them can, including really common ones like carbon dioxide and water. Unfortunately, though, I cannot show you supercritical water because that would require temperatures of at least 374 degrees Celsius and pressures of at least 218 atmospheres, neither of which I have in my home kitchen. But I do want to tell you about supercritical water because it is turning out to be a really promising way of absolutely annihilating forever chemicals. What do you want from me? This is one example of a forever chemical, perfluorooctane sulfonic acid. Now, officially, its chemical family is known as per or polyfluoroalkyl substances, or PFAS. We made a whole video about them that you can check out, I don't know, here or here, or wherever it is. But the short story is they can be super useful for making things like this or this or this. But they're not good for us. They last forever, and they are everywhere. And by everywhere, I mean everywhere. 98% of Americans have them in their blood. Ideally, we'd be able to fully and completely destroy PFAS before they get into our environment, our drinking water, and us. But when you try to do that, you run smack into the chemistry of fluorine. Now, fluorine is the master of the halogens. It is the most electronegative element on the periodic table, and it's also one of the smallest, which means that when it bonds to carbon, you get the strongest bond in organic chemistry. Look at this molecule again, perfluorooctane sulfonic acid. Remember? Of the 29 bonds in this molecule, 1, 2, 3, 4, 5, 6, 17 of them, more than half, are carbon-fluorine bonds. And all of those CF bonds, they make PFAS very difficult to destroy. They are resistant to heat. They are resistant to ultraviolet light. They're resistant to enzymatic degradation. So for a long time, the only way to fully destroy PFAS was to incinerate them. But if you don't do that right, you can actually just end up creating different PFAS, not good, or exposing the people who live close to the incinerator to PFAS, also not good. And there's a lot of PFAS-containing stuff that we need to destroy. For example, roughly 37 million liters of firefighting foam. So for the past few decades, scientists have been experimenting with a new destruction technique called supercritical water oxidation. This is a pressure-temperature diagram of water. Temperature increases this way, pressure increases this way, and the different sections on this diagram tell you the phase, solid, liquid, or gas, that water will be in at a given temperature and pressure. So for example, at low temperature, water is a solid, ice. At medium temperature and medium pressure, water is, boom, right here, a liquid. Now these lines right here, this one and this one, represent phase changes. Let me show you what that means. Let's say you have some liquid water right here, and you crank up the heat. That will push the water to the right on this diagram because you're increasing temperature. Eventually, you hit this line. This is called the boiling line because it signifies the transition between liquid and gas. As you cross this line, water goes from being a liquid to being a gas. In other words, it boils. Now, suppose you've got liquid water at room temperature and pressure, and then you crank up both the temperature and the pressure way beyond what you'd get in a kitchen pressure cooker. You've got opposing things going on. The increase in temperature, that tends to push materials to become more gas-like because the molecules have more energy. They're flying all over the place. They're bashing into each other and zooming off in all kinds of different directions. But the increase in pressure, it wants to do exactly the opposite of that. It wants to crush molecules together, pushing them to become a liquid or a solid. And at some point, the water is like, I don't know what you want from me. And it becomes kind of a distinct fourth phase of matter almost. It's not a liquid. It's not a gas. It is in between. It is both. It's called a supercritical fluid. Going supercritical can completely change a substance's properties. For example, water. At room temperature and pressure, water is a liquid with a viscosity of about 0.009 Pascal seconds and a density of about 1 gram per milliliter. A tiny fraction of it dissociates, forming ions, H plus and OH minus. And water is also polar, meaning that every molecule has an excess of electric charge on one side of the molecule. Now, those two properties make water excellent at dissolving salts, like table salt, but they also make it terrible at dissolving things like oils, gases, and many organic compounds. Oil and water don't mix. But when water goes supercritical, its density drops by 2/3. Its viscosity drops by 95%. It stops dissociating into ions, and it starts acting as if it were a non-polar liquid. Water changes its personality completely. So salts, for example, don't dissolve in supercritical water at all. But non-polar molecules like gases, aromatic compounds, oils, they do. And you know what else does? PFAS does. Dissolving PFAS is an excellent first step to destroying PFAS. And the second step is to burn them. But I don't mean burn them. Now, normally when you think of burning, this is what you think of, a combustion reaction. And combustion reactions are burning, but there are other kinds of burning too. In fact, combustion is just one subclass of a much larger class of chemical reactions. They're called oxidation reactions. Oxidation means what it sounds like, combining with oxygen. Although if you want to get super technical, you can actually have oxidation reactions that don't involve oxygen at all, but that is a whole other video. This avocado turning brown, for example, is an oxidation reaction, but not a combustion reaction. Now, oxidation reactions can be really useful if you want to completely destroy an organic molecule. Why? Well, because if you do it right, you mostly end up with carbon dioxide and water. For example, this is the oxidation of one molecule of propane. You get 3 molecules of carbon dioxide and 4 molecules of water. Turns out supercritical water is a great location for oxidation. Why? Well, first, it's hot and at high pressure, and that means that all the molecules have tons of energy, plenty of energy to break, let's say, the strongest bond in organic chemistry. Second, oxygen is fully miscible in supercritical water. What that means is you've got dissolved oxygen throughout the whole system, and that is great if you're trying to oxidize something. Third, PFAS being organic molecules, they are also fully miscible in supercritical water. So you take some PFAS, you throw it in some supercritical water along with some oxygen. What you have is a high energy system with tons of dissolved oxygen throughout, and even the strongest bond in organic chemistry cannot survive all that firepower. Researchers have found that one pass through a supercritical water oxidation system destroys 99% of PFAS in less than 1 minute. So that's perfect, right? There are no downsides to this technology whatsoever. Well, let's take a look at what happens to a typical PFAS after it goes through this process. And this is our typical PFAS. It is perfluorooctane sulfonic acid. Now, before we dive in here, I should say that all the steps I'm about to show you, they are hypothetical because supercritical water is such a harsh environment, it's kind of hard to tell what's actually happening. But it is reasonable to assume that the weakest bond in this structure would fall first. And the weakest bond is this one, the carbon-sulfur bond. So what happens when that bond gets cleaved? You get 2 things. The first thing is this sulfonate group becomes sulfuric acid, H2SO4, a strong corrosive acid. And that is problem number 1. You don't want a strong corrosive acid in an industrial process, but let's keep going. The other thing that gets formed is this chemical, C8F17 radical. And in this strong oxidizing chemical environment, this gets oxidized fully to CO2, carbon dioxide, and HF, also known as hydrofluoric acid. And if you thought sulfuric acid was bad, hydrofluoric acid is 10 times worse. It is toxic, it is hazardous, it is corrosive, it is everything bad that one chemical can be, except it's not explosive. And the funny thing is, when I wrote that description of hydrofluoric acid, I got a comment from the fact checker who said, and I quote, "Is there any way to make this more dire?" HF is the thing I still have nightmares about. It's not just that it has these characteristics, it's that the fluorine takes it to the nth degree. And then, in all caps, it will literally eat your bones. So yeah, I didn't sensationalize HF quite enough. The third downside is that it's expensive. It takes a lot of energy and therefore money to get water into a supercritical state. Now, dealing with the first 2 downsides is actually fairly simple. All you do is you take a base and you add it to the reaction mixture. And what that does is it neutralizes sulfuric acid, hydrofluoric acid, any other acids that may be present. Now, as for the uses too much energy downside, look, that one is unavoidable. But really what it means is that we're not going to be using supercritical water oxidation to get rid of every type of waste that's out there. We're going to be using it selectively on things like PFAS or dangerous wastes that can't be incinerated like chemical weapons or environmental toxins like PCBs. So is supercritical water oxidation the solution to our forever chemical problem? I mean, I sure hope so. What's not to love? It's super, it's critical, it's water, and you're burning stuff. We should do supercritical water cremation. No, we should not. That is a bad idea.